start up?
I think we can go ahead and get started now. I wish Nick had told you that you need to install Couchbase and try it out to get out of the parking garage, because that's the true answer. But anyway, so I want to introduce our speaker here. This is Curtis Wong. He's a data scientist. He's now at Facebook. He and I worked together when we were back at SAP, and he was a data scientist on my team. Great guy. He's since worked at Yahoo. Been in Facebook for about a year. Is that right? About a year. I asked him to come in and talk about machine learning. So I think this talk is going to be about the topic, focusing a little bit about the infrastructure, giving you some of the real-world insights that Curtis brings from his experience. It's not going to teach you about the intricacies of Facebook's private stuff that you're not supposed to know, but I think it'll be, other than that, it should be very, very interesting. So Curtis, why don't you take it away?
All right, thank you, Will. Hello, everyone. I'm Curtis, and I work on machine learning problems at Facebook. So the recent project that I'm working on is ranking public content, so the content ranking problem at Facebook. So a little bit about myself, and thanks for Will's introduction. So I started my career in robotics, and then I joined HP to work on some pricing and optimization, and ever since then I work with Will on big data, Hadoop, Spark stuff, and then I moved into machine learning and data science at Yahoo. So I was doing the display forecast for their guaranteed display advertising business. And then I started to work on the sponsor search, and now I'm actually with Facebook. So today I'm really excited to talk about something that I feel great about, which is machine learning, and I'm fascinated by this subject. So as well, probably mentioned to you, I'm gonna divide the talk into two parts. The first part is about more on the machine learning practices and over the year, the lessons I've learned along the way. And then also some of the infrastructure that I've seen in these companies. The second part is something that actually is the latest hot thing. I don't know if you guys are into deep learning, but I would like to talk about deep learning a little bit because that's the next kind of big thing in this world. Okay, so who here uses machine learning on a regular basis? Okay. So basically, I hope you are here because you know that there are great advantages that you can gain from applying machine learning in your business. So I don't know, like all these popular Silicon Valley companies, like big companies, they have been using machine learning techniques behind the scene to optimize for certain objectives, like their business metrics. So learning from the pattern of data and also using some statistics to basically rank candidates and products in the case of Amazon. And then you can also know the big Netflix challenge. They actually analyze all the user behaviors in order to recommend better movies to you. Okay, so machine learning is actually a pretty interesting topic until now because even though we know these can make a difference, but it was really hard before to actually implement machine learning. And the reason why it's so popular, there's a couple of reasons. The first reason, I think, is because the cost of storage and compute has gone down a lot over the past years. So now, you know, with the big data technologies like Hadoop and Spark, you can actually you can ship your algorithms to the data, so in a sense, distribute your compute. So that actually saves a lot of cost, and it makes it possible. Because in order to actually get a good machine learning model, you actually need a large amount of data. So Peter Norvig once said, you know, more data beats a better algorithm. So that's also one of the reasons. And the other thing that I want to mention is also there have been tremendous strides in distributed computing. So like the ones I mentioned, MapReduce is one good paradigm that everyone is familiar with. And also recently there have been parameter servers where you can actually do distributed parameter update in the stochastic gradient descent. So all these reasons combined allow us to do machine learning. Okay, so when I usually talk to my friends about what I do, who is not in the field, they always think that, oh, you are into this machine learning and this AI world that eventually you're gonna destroy the world. So a general misconception is like, oh, these machines are gonna have intelligence. Some do, but not like humans, right? So we're working on the field that's not gonna destroy ourselves or like take away our jobs. At least that's what we're trying to do. So you think that everything's very cool, but in reality, when you mess it up, you actually you want to build a machine that actually helps you. And this is one of the graph I used to remind myself that machine learning is not just black box thing. You plug it in and then it will start working. So what I used to explain to my friends, and I'm sure a lot of you have seen this Venn diagram 1,000 times. So machine learning is a very specific field that actually composes several domains. So first of all, you need to have some statistics background. You need to know how these numbers can work together to your advantage, and also you need to be able to implement it. So that's where the engineering comes from. And most importantly is the domain knowledge. It depends on which task you want the machine to be able to solve. You need to come up with some kind of features, right? We call features. And usually some domain experts will have more knowledge in this, like what we can think of it as a predictor. So you need a lot of domain knowledge in order to be successful. So machine learning today, at least right now, is very good at specific tasks. So I can have a machine, I can train a machine learning algorithm to tell me good emails from spams, right? So it's a very specific task. Maybe I can teach a machine learning model to recommend products to me based on my past behavior. So that's also very specific. So machine learning nowadays is not like a generalized intelligence kind of thing, but it's more like for specific tasks. And in order to have that, you actually need to get quality data. So garbage in, garbage out, right? So in order to show the machine how to do certain things, you need to usually give them good examples of how to achieve a specific task. So that comes down to also the feature engineering part. This is the part where I say the domain knowledge can apply and also the creativity can come from. So a lot of data scientists, most of the time they do is to, I'm gonna show you in the typical workflow, is basically come up with a hypothesis that you want to try, a problem that you want to solve, and you need to first start gathering data. So there's whole ETL, what we call ETL, but it's basically data cleansing, data formulation, starting from unstructured, structured data, and then how do you put it into your data frames, like rows and columns, that you can start training this model. So all these kind of things will happen over and over, and it actually takes iterations of experiments in order to get what you want. So that's kind of where we are today, and of course I'm gonna talk about deep learning, which will overthrow some of these statements, but we can talk about that later. So this is a typical machine learning workflow, so just to give you guys an idea who doesn't use machine learning every day. So like I said, it starts with you having a hypothesis. We can say, I'm going to improve the click-through rate for this particular app when a user enters this query into our browser. So that's kind of, that's my goal. In order to hit that goal, then you need to start having some kind of hypothesis, right? Though you probably want to model user behaviors first, right? For this user, I might interact with, for example, I'm a big sports fan, so if you show me like 49ers or Warriors t-shirts, I will engage more. So you can come up with this hypothesis, and then you want to formulate a problem. So you want to start writing basically how you're going to achieve user modeling. So user modeling by itself is a research topic. So you can start thinking about different ways that you want to go about this. Okay, so let's say, for example, I'm going to do a user modeling that helps the CTR, helps to drive the CTR of a particular app. Then what kind of data am I going to need? Right? So that's kind of the next step. So you want to say, I'm going to build a machine learning model for predicting CTR and from like personalization, from understanding the user. So you probably want to gather some user history, right, or user interests. So this is not really easy task. Obviously, a lot of people like myself before were stuck in this step because I want to try something, but I don't have the data, right? So there are different ways you can go about this. You can, try some open source data sets, and there are some available that's on Amazon. You can look at it, and then you basically want to synthesize it. So there's something that you want to also mix with your objective. And then, so you kind of want to do this workflow, and you also want to get some statistics from this data. By statistics, I mean like whether or not it's significant enough for something that you want to test. Okay, so this data preparation obviously is very hairy type of workflow that you still need to clean this, and sometimes there are some missing values depending on how you get the data. So in order to obtain this is actually, I remember someone was saying that 70% of the time of a data scientist or a machine learning practitioner, the time is spending on this step, like getting the data ready. So if you guys have done it before, you would know what I mean. Okay, let's assume that you were able to get all these data. The next step is the feature engineering part. So this is where domain knowledge will come handy. So let's say if you are an expert in, I don't know, human psychology, then you would know that, guys react better to the color red. No, I'm just giving you an example. This is not necessarily true. But I like red sports cars, so I'm just saying that. It's true. But I'm saying, so let's say like I like red cars, and then that would be one feature, right? It's something that the machines would not have known, right? So you can say, hey, how about the color of the ad, right? Or one thing I know for sure is like beautiful pictures everybody likes, right? So, or people naturally like videos that moves, right? Something that interests you. So something like that, then you start throwing these features into your model. And this is where the creativity comes from. This is where you are allowed to teach the machine how to learn it. And there's the next step is the model training part. So now you have a lot of different ways that you can go about this. So for a classic categorization problem, you can use like boosted decision trees, you can do random forests, you can do SVD. So there's different ways, depending on your problem, you might want to try different algorithms. And each algorithm will have these hyperparameters that you will need to tune. But nowadays, I think the state of art will allow you to do parameter suite. That's basically a neighborhood search that allows you to find probably locally optimal solutions for your parameters. And this is a step where you need to care about overfitting and underfitting. So sometimes you think I learned a lot from the data that I selected from. I can perfectly decide, like I have a perfect precision and recall. But sometimes you might be overfitting because the sample you get may not necessarily reflect the entire population, right? So this is where you need to keep your model learn the right thing, but in the meantime, try to generalize it. Okay, and then what we do usually is we will do something called like offline evaluation. Depending on your task, you will have different metrics to measure your model's performance. In the information retrieval type of work, or classification, binary classification, you can do position recall. And then there's also the area under the curve. And for search, there's also the NDCG that has been used to determine the rank. So something that this is actually, so I don't know if it's big enough for you to see, hopefully. This is actually a cycle. So you actually do this in short cycles. So you keep testing your new hypothesis. Hey, how about this idea? How about throw this thing? How about I train this? And then you look at the result and just keep improving it. And usually the companies, at least the companies I've been to, you actually do this offline. So you simulate, you kind of get this data, and then you simulate offline, and then usually you would present the candidate to a review meeting, and then they will actually say, hey, whether or not we can allow you to test this online. Because online means you're gonna kind of take a small percentage of traffic to try this new model that you have at your hand. So that's the next step. So the next step is basically you would be able to take a small percentage to validate against the offline model that you have trained. And this involves a lot of bucket tests or A/B testing. So you basically compare with the control, and over a period of time, whether or not you have beat the control, and in what way, and what kind of metrics that you look at. And usually people will define the launch criteria, like you need to beat this metrics by how many percent, and the counter metrics cannot be like, you cannot regress on the performance and stuff like that. So there's different metrics that you evaluate. So performance impact, so for example, your model can be very sophisticated, and then you might not meet your performance requirement, like the QPS requirement. So if the user comes in and it takes like 10 seconds, 10 minutes, 10 seconds is long enough. 10 seconds to load an ad, and that's obviously not gonna work, even though the accuracy is very high. So there's things that to consider. So this is just a typical machine learning workflow, and I think I pretty much covered everything. So that was from the process point of view, and I'd like to take a step back and look at the engineering point of view, because they are a little bit different. from the engineering point of view, there are many different challenges. And I think each of these blocks here by itself can be a research topic if you are really into this area. So first, it starts with data. The challenges usually come when you want to process a large amount of data, right? So as I mentioned in the beginning, more data means a better algorithm. So you usually want to have a lot of data. So first of all, you need to figure out a way to store them, right? And then to retrieve them. So that's where the distributed file system comes in, how people can actually distribute the data and retrieve them in an efficient way. So that's kind of the area that you would work on if you are interested into storing, partitioning, sharding the data for faster retrieval. And I'm sure Couchbase has a good solution for that. The next one is algorithm, right? So you also want to think about like different ways or the improvements in an algorithm that allows you to do things distributed. So one example I can think of is I think Spark has been, not Spark, yeah, Spark, the project, open source project Spark has been porting from, usually earlier there was some good libraries from scikit-learn, from R, like a lot of these you would run on a single machine and then they would try to distribute it. So that's basically, if you look at their code, that's what they're doing essentially. They want to allow the code to run in a distributed fashion so that you can train on a lot of data. So there are many ways to do that. Now, one of the good ways to do is think about how you can distribute the work and just keep everything that requires a lot of data on the worker node, and then you want to have, so this usually involves steps, right? So you want to do like a announce, and then the driver will actually send all the work to worker, and then each worker will look at their partition of the data, and then they'll try to train something and then send it back to the driver, and then driver will continue the next iteration like that. So something along the line. So MapReduce is one example, right? So you say, hey, I'm just gonna map everything on each worker node, and the reduce step you say, okay, now tell me the result, and then I'll send it out again, right? So that's kind of one distributed way of thinking out. Now, training model is also a very interesting step. So there are a lot of different models that you can use, and people usually have different ways of combining them, right? So some models are good for capture linearity. Some you can have some non-linearity in the data that you can combine different kind of models, and so that's also one step you can think about when you deal with a large amount of data. Fault tolerance is very important. Like, what if I want to run like iterations of, so usually machine learning involves like training and iterations. What if like at the end, like the final step, I actually lost my data? Do I have to restart over again? So fault tolerance is also very important. That's why Hadoop has this three-way replication, and then Spark has this distributed RDD, resilient distributed data set that allows you to recover when something goes wrong, because it will go wrong. If you start training on thousands of cores, right? Like by statistics, something will go wrong. And then it's either like running out of memory or the disk is failing or whatever. So something that will go on in a system point of view. Finally, deployment. So deployment is something that you don't usually think about, like at least from my point of view. I always think about like the model performance and how do I train a better model and make sure that everything is good according to the business metrics. But deployment itself is also very important, right? How do you maintain this model? How do you update this model? And whether or not you can actually serve the model, like the QPS example I was telling you. Like if I simply have a very good model, but it requires a lot of data, a lot of computation in runtime, then that definitely is not doable. So people have different ways. I was just at a talk at KDE, and I think even LinkedIn ran into this problem. They have a very nice model, but now they need to decide how do I get an estimate of the model, because they cannot get the whole picture. They just need to basically cache some of them and use some sketch algorithms to get an estimate, right, of what to show to the user in the end. So even deployment in itself is a challenging task. So as you can imagine, there's different areas, and I'm sure you guys are very interested. So these are just the type of areas that you can look into if you are really thinking about implementing machine learning. Okay, so here is my I kind of want to draw it on my own, but I don't think I do a very good job. But this is based on my experience, what a typical ML infrastructure, without giving away proprietary information, of course, all the material has been vetted by the PR at my company. So basically, I just gave you kind of an abstraction of how things will usually work. So this is the ETL part I was talking about. You usually have some data store. It can be a SQL database. It can be a NoSQL database. It can be a distributed file system. Usually you want to store data somewhere. And when it's large, you usually store it in disk. And then when it's small, you can fit everything into memory. Or Spark that loads from memory and keep it in memory. I mean, loads from disk and keep it in memory. Doesn't matter. You still have some kind of data store. And usually you would have some kind of daily pipeline. Not daily, but or hourly. That depends on how often you use the data. So for example, if I'm calculating, if I'm gonna train a CTR model, there has to be some kind of historical data of, given a user in an ad, whether or not this ad was clicked, right? So you wanna have a daily snapshot that gets updated overnight, usually. And then so that allows you to do some ad hoc analysis. So how did I do yesterday? If I just deploy a model, then you can look at all these metrics. So this is where Spark SQL can come handy. You can load from the snapshot. You can run some SQL statements and see, basically find these features. And at Facebook, we use an in-house tool called Presto for that. So now you start, running some analysis, and then that's the part I was talking about. You usually will have some kind of ML framework that allows you to train. And it's good that you can actually load it from the snapshot. So if it's in HBase, if it's in HDFS, or even in Hive, you usually have some kind of connector that allows you to just pull, hey, the daily snapshot from yesterday, and then let's start training. So you'll be able to pull it into your ML framework. So I listed some of them there, but it's not limited to that. You can take. It depends on what kind of thing you want. So most of the example I gave you, they are distributed because usually you want a lot of data. But obviously you can pull a spreadsheet from SQL and put it into R. Right? So basically that's the same thing. So there's some ML framework, and then that's how you train it. So and then the next step usually is you want to cache some of the results. So that's the part about starting thinking about deployment, right? So that's the last step. You usually, once you have the model trained, you want to store it somewhere. So during runtime, you can quickly retrieve it. So, right? So that's something that, given a query, I'm not gonna run 1,000, steps in order to find out what are the candidates, right? You usually just normalize them, not denormalize. Normalize them and then just cache them into a key value pair. So for this query, these are the best candidates based on what I know since yesterday, right? And then you just cache them somewhere, and then why I have another database is usually the real-time features. So sometimes your model rely on something that's more, it needs to be more current, right? You can get most of the feature from the snapshot. But sometimes, hey, how about I have something that really shows the trend, right? So if something is trending, then I really need that. Otherwise, I wouldn't have known from yesterday if this event just happened, right? So there's usually some real-time counter that's sitting somewhere. If you look at all the papers on academia or from industry, they usually do something like that. And then you just merge from the world that you know from yesterday with what's happening recently, and then you send it into some algorithm service. I came up with the word just to abstract it. So basically, when a request comes in, you take from the model score, you merge it with some real-time features, and then you say, hey, that's my final answer. So you will send it back to the cloud, so that's cloud is where the whole thing starts, right? The request comes into your system. And then usually you would have some kind of logging, hopefully, right? Because you want to be able to know how well you did or how bad, and then so that you can actually feed it back to your data store. So this whole thing can start over again. So this is like a very, very high level view, abstract view of what the industry have been doing, and I think this is still the case. So even though things can change, technology can change, but at the core, this is what we do. And you can always go back to the abstraction if you want to know more about each step. So this is kind of a more realistic view of the previous diagram. Very good?
Quick question.
Yeah.
On this snapshot, I missed the part, exactly what is snapshot, how far do you go?
Oh, it depends on your model. So people tend to do daily partition, and because that allows you to go back into 3 months or 6 months. So usually from the snapshot, your ML framework can say, right, go to the past 30-day partition and pull everything if it can fit into your framework, right? So usually they are partitioned by day, at least that's what I know. There are some sub-partitions. If the data is really big, maybe they can do it by regions. It's a typical database partition scheme. But yeah, so let's say your data is not very big, then you just do it by day. And that gives the flexibility during the ML framework. You can say, I want to select my training data. You can just say a SQL statement that gives me partition up to past 30 days, right? So snapshot is kind of a source of truth. But in ML framework, you can say, this is the training data I want to collect, right? So it gives you flexibility in both worlds. And also in the ad hoc analysis, you can also do the same thing. I just want to look at the 3 days, and then in the end, when I want to train, I can say past 30 days, right? Because they are all there, partition by day. Yeah.
So what criteria do you use to determine when to retrain your model?
Oh, this is a great question. Usually this depends on your business need. So for ads, you usually need to train model more frequently. Not because of the CTR, because CTR doesn't really change much, but it depends on what hypothesis you have that might improve the model. So typically, like if it's a historical thing, it's very stable, then you don't need to retrain. And then usually they have an ensemble method, so I didn't mention. So usually you will have some different submodels that's in charge of like predicting certain things. So like the CTR problem, of course, at the final layer, like it is your final objective is to get click. But this may be divided into many different problems. Like one thing I was talking about is modeling user, right? So the modeling user part itself can be a machine learning problem. Then you probably can train it more often, right? Because the user may gain different interests based on. So you want to be able to make sure they are actually in different blocks, so it's easier for you to play around with. And then the final model can be trained, based on your baseline. You can say, okay, I want to move my baseline every 2 weeks. So each submodel, if you think you're contributing, then let's all come in here, and then let's build a new baseline, and then do that test. But this is when it's tricky, because your different submodels may interfere with each other. Individually, they are great. When they're together, so that's why all the way in the beginning, you need to find out a way to do bucket tests correctly. So I have some gotchas there. So challenges and lessons learned, that's one of them, right? So you kind of want to have a back bucket that always keep track of things before your change, right? That gives you a source of truth of whether or not you actually have interaction between the submodels. So that's a more deep topic.
Quick question.
Yeah.
What exactly are we feeding into the data store? And the process from data store to the snapshot happens whenever new data comes into the data store?
No, usually this, so first question is, what do we actually store in the data store? So you can see there's a dotted line, the login service that feeds in there. So data store can have static information, and also these information are from, since the past day, what were my clicks, and who clicked on what. And so those dimensions are determined by either data engineers or data scientists like yourself or machine learning practitioner. You can all work together and say, hey, these are the metrics I want to collect. So there's usually an ETL. So ETL is like, I run all the time on schedule. It's like a train. I'm gonna move in from this snapshot, I'm gonna move to the next watermark, if you think of HBase. Like from this watermark, I'm gonna move to the next watermark, and I'm just collect everything. Yeah. Okay. So there are some challenges and lessons learned. So one thing, the interaction between submodel, that's definitely one. The other one I have along that line, because now that's my line of thought, is run some AA test. So people always talk about A/B tests, like bucket tests, just to see the differences between test and control. I encourage you to always keep one as AA test. So it's nothing changed. Okay, you didn't do anything. And you'll be amazed to see what would change like in the AA test, right? So sometimes logging was wrong, sometimes something bad always happens. Or like your sampling was wrong. Like you were always sampling user from California instead of, it should be like distributed, but you were always actually getting all the impressions from California, and the whole thing just went down. So I encourage you. So I always think about doing AA tests, because that will capture instrumentation errors and also some other stuff that you would not have imagined. So ad hoc analysis is something that I think is very important, because it gives you real-time feedback. And usually, so if you look at it, we have real-time feedback. Spark is in memory, so usually loaded somewhere in Presto is also near real-time. So this allows us to iterate faster. You also want to know what happened yesterday and how can I do better, right? So having this capability is very important. So when you design the ETL, if you are a data engineer, you want to be able to allow the engineer, the machine learning and data scientists to be able to do that. Right? They always want to look at the data, but how do you present it in a way that's easier for them to integrate? The other thing is adding features. So, right now I'm gonna try something new. I really need this feature. I read it from my paper, and this is really good. So how do we add them? And then we need to go the whole thing of adding this new column in the data. Like, okay, so it depends on how it's designed, right? So if it's really robust, you can always include new features, and even better, you can do a backfill, right? So, this new feature, how do I collect? So I started adding this feature yesterday. How do I collect all the way up to last year, if that's my training span? How do I backfill this dimension of data? So just things to keep in mind, because that will be, in the end, very important. And this is the challenges I faced. Okay, and then the third one is always there's gonna be a gap. So your sample is not the entire population. So you have to keep in mind. Machine learning, you train on the sample data and you try to generalize it. So it's always different from the online environment, no matter how good it is. So there's always gonna be some gap. And so what I mean by gap is like, my offline result accuracy is very good, like 90% right, accurate, but when I try it online, it's like 40%. So, when this happens, you just have to keep in mind, there might be something going on, right? It depends on how you sample the data, or maybe your feature is really different, so you need to rethink the problem over, right? So you don't want to just, think that, your job is finished at offline level. So you always need to think about the next step. Yeah, so the system and other issues, that's something that I mentioned, right? So you always need to think about different ways that can mess up your metrics and your results. Okay, so I think that's the first part of my talk. So this is basically all the machine learning problems I have run into, and also in my mind what a typical ML system would look like. Okay, questions so far? Are we good?
So in your experience, what techniques have you used to fill in missing data?
Missing data.
Yeah.
There are different ways that you can deal with it, right? So typically, if your data set is very large, you can just get rid of it. The other way you can do it is you can encode it in a way, right? So you can do an encoding saying that this is a missing data column. So you just group them into one category, right? So if your column has this, if your row has one column missing, you can group, like you can say, this is a third type. You can make it a categorical feature, right? I don't know. Because missing doesn't mean anything to the computer. It can be, this is a good sign, it can be a bad sign. You group them into one category, right? There's also something you can do. You can always give it a mean, or a linear feature that you can give it, right? So you have to try it out. But there are different techniques. Yes.
What does it mean in the problem statement of your predictive models? Like, are they trying to classify something or recommend something?
Oh no, this is very general. So it doesn't. So I'm trying to describe a general type of workflow. So it can be a classification problem. It can be a regression, usually they are category. So what I mean is they are usually classification problems. So given an input, you want to say whether or not this is. In the case of binary, you can say whether or not this ad was clicked or not. So you are trying to predict the probability that given a user and ad pair in a query, usually in sponsor search setting, whether or not this ad will get clicked. So that's a probability, so you can think of it as a classification. So you can say either 0 or 1. That, in the end, that's your label data set. But this can be applied to general recommendation. It can be matrix factorization, but you still need to go through the same process. So it depends on which one. Yes.
I don't know if this is maybe a better for the end question, but I'll go ahead and ask it now.
Sure.
So I wonder if you consider the fundamental problem that the better your algorithm gets at getting people's attention, the more they start getting pissed off and installing ad blockers. I know in my case, I always use ad blocking, and anytime I install a fresh browser, I start surfing around until I hit that website where the ads are the most obnoxious and intrusive, and then I say, oh, I gotta go get the ad blocker. And I know it's a big problem that the trend is for more and more users to be Alpha Sierra, Sierra Hotel, Oscar Lima Echoes like me, and say, no, I don't care about your ads. So is that a problem that you guys have been interested in or looked at all?
Yeah, that's a great question. So just to be clear, I'm also on your side, even though I'm working on as IoT ad blocker. But so that's actually not a problem for me because I'm just optimizing for a objective function in my case. Like my work is about, I'm not working on ads anymore, by the way. That was my previous slide. And so, but I was just using that as an example because everyone is familiar. I think there are some user research that's been done. So that's outside the scope of the talk of the machine learning world, because the machine learning is just like, give me this problem, I will solve it the best I can. But like in terms of user retention, that's also very important, right? You want to show contextual and relevant ads to a user. Like you can still sugarcoat it. Like if you don't like ads, you won't like ads. So like me, I don't like ads. But usually what the user researcher is trying to find a balance is like they will also run a bunch of tests, right? So they might actually run some tests where this group of users won't see ads versus this group of users will see ads, and then they see their user retention. Maybe I try it once and then I never come back. Then they say, okay, I'll piss off this user. And then they will try to balance it in a way. So there's another side of the science, which is modeling user behavior and whether or not they like it. And then you can probably have a filter that I don't never show ad to people who are pissed off with our product, and then show some. So I'm just saying that that's another research area.
Yeah, I got a question about the ad hoc analysis. Can you keep a process? How does it work? And also give an example in your work. How does it apply to?
Okay. So ad hoc analysis, it can be done for two purposes. One is usually you want to debug something is wrong with the model, right? So you train the model, you're coming from the same snapshot, right? So the snapshot will feed into your model and also to give you like a view into it, like what's happening. So you can actually debug what the model is doing wrong by running an ad hoc analysis, right? That's one thing. The other thing I think is very useful is to explore and find new features. Like you want to find strong predictors for certain tasks. And sometimes the machine will learn for you, right? You can just feed everything in. Sometimes like a GDBT, they'll tell you the feature importance. So what you would normally do is you just put 1,000 dimensions and then try, hopefully cross your fingers that they will learn the features. But sometimes they don't, right? So you need some manual intervention. That's why you go into some ad hoc analysis. So maybe you're showering like in the morning and then decide, hey, that's a great feature for clicking ads. Then you just go an ad hoc and say, okay, let's see the percentage. And you can see the histogram of how this performs against the sample that you have. So this is kind of like diagnosing and like debugging when things go wrong.
Can you go over this and tell me where the most cost actually spent, effort or money? Like which bucket there is actually cost the most, and where to prepare to spend more money, more effort, more time, more people.
Okay, so I still stick to the number. So in terms of effort, the feature engineering and getting the data. I'm getting the data into the right format and finding that particular feature that you're interested in. So data cleansing was one of the biggest problems because sometimes you get weblog data, which is super unstructured. They're just text files, right? And then you need to extract, for example, the user agent or cookie, stuff like that, right? So then you need to write your custom SQL script, or sometimes you write UDF, user-defined functions, and then you can load from HDFS. So that's also one part. So data preparation is the biggest, at least from what I heard from data scientists, that's the most time spent. But in terms of money, that is an interesting question. I haven't thought about that, because when things go really big, like at let's say Google, Yahoo, or Facebook scale, then it might be here when you are actually distributing your key value store. That might be something that you want to think about, right? Or how do you partition the data, right? And how do you deal with the QPS constraint, right? For something comes in, I want to immediately have the result. Then that means how many cache layers do you have, right? And then you're going to calculate the miss rate. So that is also another thing that's beyond my expertise. So something that's to think about. Okay, I don't know how much time do we still have, maybe.
Go for it.
Okay.
People are here to see.
So nowadays you cannot go to a machine learning talk without talking about what's really interesting to many practitioners. It's called deep learning, and why I had a Lego block here is I will explain later. But visually I want to represent this: how deep is your network? So the deepest you can get. So if you want to talk about machine learning, you have to first talk about embeddings. So who is familiar with what an embedding means, or representation? Yeah. So usually you have a discrete object and you want to say that I want to map it to a vector space. I'll explain why we want to do that later. So usually your input can be words, it can be pictures, it can be people, it can be anything, something that you want to model. But they are discrete, right? You cannot say, okay, what's the weight of that word? So this is where embedding comes very useful. It can provide a function that maps from a discrete space to a vector space. So the key property is to preserve similarity. So let's say these two words are close, or these two people, they are close in real life. In their vector space, I want them to be very close. So you're actually capturing the essence in it. So in a sense, you're capturing the reality and what's the interaction between two objects in a real world. Okay. So I think I just said that, right? So you want to be able to generalize from discrete objects, and you want to be able, so it allows you to use vector space algorithm, because computers, they think math, right? So if you can put everything, a discrete thing, into a vector space, then they can do matrices, right? So it's easier for you to do classification, regression, that kind of stuff. Most importantly, they are the founding block for their building block for complex model like deep learning, right? You need to be able to represent something in vector space in order to do deep learning. Okay, so I'm just gonna quickly go over this. This is an experiment. I hope Huccardi. So who here knows what Huccardi means? Okay, good, because it's not a real word. It's a fake word that I cannot wait, and I hope I tried to look it up online. There's no such word. So I just have following sentences. So Tom put a dish with Huccardi and crackers on the table. Huccardi and butter are products made from milk. The mouse was lured into a trap by a big piece of Huccardi. So I'll just keep reading. So now, who knows what the meaning of Huccardi is? Okay, awesome. So this is what the whole embedding thing is all about, right? So you want to be able to understand what Huccardi, you want to help the computers understand what Huccardi means without giving by learning the context. So, right, you can use the neighboring words to figure out what this actually means, even though the computer doesn't know what it means. But by looking at things around it, you know what it means. So that's the basic idea of word2vec. It was very hard a couple of years ago. Basically, this algorithm is a skip-gram diagram. So basically, idea is very simple. You just want to predict, right? You want to maximize. Given this word, you want to be able to predict its context. So there's two different models. There's a Seibao model, continuous stack of word. It's the one that I just described. Given the neighboring context, can you say what this word is? So it's trying to minimize that gap. Okay, so this is a skip-gram diagram. So I think next we'll show you some interesting demo about running word2vec in Spark. So this is something that's interesting. Okay, so I didn't talk about deep learning yet, but having these embeddings or representations of discrete objects allows you to start building something really cool. So, the output of word2vec is, for a word, you can map it to a vector, right? So these vectors, you don't necessarily have to train them, although you probably want to train them using your own data. But usually, I can just get the output of someone who has done it before using Wikipedia. So these are like semi-structured thing, right? So it doesn't, you can just train from corpus, right? You can just ask a computer to keep reading each text, and then by predicting the neighboring context, it gives meaning to this word, and then you can generalize it to every word. Then you take this whole word and its vectors, and you can use it for something else, right? For example, you can use it for classification. You can say whether or not this query and this particular text, they are relevant, because now they have meanings. So I didn't show you. In the paper, it was describing, right? So for example, after this is all done, they train it on the Wikipedia or other corpus. So for this given expression, you can take the vector or the embeddings from Paris minus the vector in France plus Italy. And the closest you get is the vector of Rome. So you're giving semantics to these words now. Before, it was impossible for you to train with the word, right? So how many words are there in English, like the most commonly used, right? There, I don't know, thousands, right? So you do one hot encoding on these thousands, and then you do combination with other features. How do you train with this? But now they are very nice and neat. They are just a 300-dimensional vector at the end of the word vector. Then you can use it for whatever purpose you want. So they actually capture the semantic meaning of a word, and then you can use it for a building block. So I think Will will talk to you more about that. So I just kind of only have 2 slides I want to talk about. So deep learning, everyone is thinking, oh, now everything is cool, right? You can learn embeddings for pretty much everything and then apply different deep neural network. So I was just mentioning that you don't need to train, you can train your own model, but now if somebody gives me that embedding, so it's like a building block for me. I don't need to know how it's generated as long as you preserve those similarity features, right? I can take the output of that and plug it into my model. So this is where the Lego block starts to make sense, right? You can take the output of something and then you can plug into the next layer, and then they can connect to the next layer, and then you do backprop to basically train your weights and then to achieve your final objective. I know this all sounds really unbelievable, but the whole hype actually begins in the computer vision world. So this is a paper from 2011, describes the basic convolution net architecture. So you can see that all these little blocks, they literally are matrices. So you basically want to be able to, so this max pooling, so you can read more about it, is basically to gather, do a dimensional reduction to gather the neighborhood context, similar to Word2Vec. You look at your surroundings and then you pick the most significant piece of information and you keep extracting it, and then you just keep doing this until you actually shrink the entire big pie into a single vector, right? And at the end, you can do differential equation, to do back propagation to calculate the weights. So that's the whole idea. You just kind of want to keep doing this. So they actually show very good results in computer vision. So that's kind of 2011. So this is very recent. This just happened, 2016. So just to give you an idea of different network architecture you can play around with, right? Once you have these embeddings, they are just matrices and vectors. Now you start to plug into different algorithms. So this is a more recent paper, 2016, from ICML. So basically you have 2 sides. This is getting very interesting because on the one side you are trying to generate. So they call it the generator network. Each of this is similar to the COMDEN I was showing. So you can start having these architecture now, right? So they are building blocks. So this generator is a COMDEN. The discriminator is also a COMDEN. But they are training on 2 different objectives. So the generator is trying to fool the discriminator. So it's like adversarial network. So it's trying to look at some images and trying to generate its own image. And the discriminator objective is to tell real ones from fake ones, right? So they are teaching each other. You have 2 networks that are just kind of, this is a brilliant idea. So if you can look at it, this is all from the paper. You can read it if you are very interested. So only the top left corner is the real training data. All the rest are generated. So given this text, the small bird has a pink breast and crown and black primaries and secondaries. So it's really hard to see here, but all these are generated by the network. And even the flower. So it's able to map word description to coming up with an image that match your description. So it's there. So it's very interesting. So now you're really getting into, and then, so for example, if someone trains this network for me, right, I can take the word embedding and image embedding because they preserve very good contextual information. I can take it and I can do it something else. Or I can plug another hierarchy behind it to do something else, right? You can have 2 adversarial, right, discriminant networks and against 1, or something like that. You can just keep, putting these blocks together. They're just matrices, they fly around. And if they follow the chain rule, right, the one output of another, you can do backprop. Everything is seamless. So just something to keep in mind. But deep learning is not everything. I just want to say this is a hype right now. If you go to any machine learning talk, they'll talk about this. But in nature, they are very expensive because they need these heavy GPUs. They do a lot of matrices operations. And they still, right now, lack interpretability of the model. So you don't know how it learns, right? They are all just these layers of matrices and some values, some nonlinear units, and then they come. And the last one is also very important. So our brain actually consumes very little power. I think it's just 2 watts or something. I don't know the exact number. But these machines, they are energy hungry. So they are really sucking up because you train these in weeks, right? And everything is just crazy. So just some challenges and areas that the researchers are looking into. So yeah, I think that's I think I'm about on time. And I think I'll just wrap it up here, and I'll stick around, and if you have any other question, I'll be happy to answer.
Do you want to take some questions?
I can take some questions now if you guys are interested. Yes.
I would have a quick question. Like you said, most of the meetups now around machine learning, they talk about deep learning for a long time, mostly focused on image visualization, in particular in cars and stuff like that. But recently we went to a meetup in H2O, and they talked about HTM, the next generation of deep learning, which is not deep learning. It's hierarchical temporal memory representation for vectors that is focused mostly on kind of looking for some issues and kind of not pattern recognitions in essence. So have you heard of this? Have you used this? Is Facebook evaluating these options as the next gen deep learning kind of thing?
Yeah,
Which is
so
closer to the biological representation from Numenta is the company behind that. So
H2O, yeah, I think I've heard about.
not H2O, Numenta is the company behind that algorithm. It used to be an institute, it was more focused on research. Now they're trying to kind of monetize this next gen approach.
So I have heard about H2O, but not the other one you mentioned. And internally, Facebook actually has its own proprietary tools that's doing the same thing. So just like TensorFlow, you can imagine, but we just haven't.
But that's deep learning, and that's for neural networks.
Yeah.
HTM is a different story.
Yeah, I haven't heard about
Oh,
that.
okay, so I was wondering if you've heard about this. This is closer to the biological representation of the memory in the brain. As of now, they're interpreting that basically as a single dimensional vector. They're still not able to get it right.
Okay. So it's still very early stage.
No, I would say the company was founded about 8 years ago, so the concept is not new at all. So I was wondering, it's more kind of oriented towards anomaly detection instead of image recognition. So it's another interesting thing that I learned recently. So
Awesome. Yeah, I'll look into it. Yeah, I haven't heard about it.
Okay.
Yes.
I think there was some hype about that, but they haven't delivered any real results. So.
they have results right now.
I'm not-
Because there was I was on that like a month ago. So they're trying to
I
commercialize that
I
too.
heard of that one. I did some research, but I haven't heard many success about that.
It seems they finally they were able to do so. So
I don't think most people can even hear you guys though. So are there other questions for Curtis while he's here? I have a question for Curtis. There's a question.
Yeah, this is a better machine learning question. I don't know, are you familiar with the book, The Master Algorithm, by Pedro? Anybody heard of it? I can't remember the guy's last name, but he's working on because each algorithm, maybe it can solve this problem, but it's terrible at everything else. So he's trying to come up with algorithms that maybe that are bringing the different schools of thought together, and hopefully can have one algorithm that will do pretty well at any problem. Do you have any thoughts on that? Is that a good idea, or is that silly, or what do you think?
I think there's a lot of research area. I mean, a lot of research in that area. So being able to teach the machine learning models to learn. So learn to learn. So this is one example. They are teaching each other how to learn. So there's also a whole school of research that's around like basic blocks of units, and they just want the machine to look at examples and learn from these basic units. So you can think of basic units as addition, right? So you just want to abstract everything into some kind of machine instructions, right? You do the swap and then you do this. So they can map it to something that the machine understands, and then by feeding the examples, you can actually ask the machine to learn the best algorithm to solve the problem. I know it's all very abstract, but you are looking at basically something, the instruction assembly code that the machine understands. Then you give it a set of objectives and you hook it up into this neural net. Just like they have like brain, small brain. They kind of want to look at the examples and try to achieve it. So there's a one. So the machines are really good at learning like video games. I don't know if you have heard. There's a lot of like machine learning video that you can look at. They just train with 3 iterations that the machine master how to play this Atari game, right?
Yeah, I heard.
Right.
about
So
that.
they just have a bunch of inputs and then just kind of basically, hey, I want to combine this input and I want to look at it, and so stuff like that. So this is also very similar, but it's more abstract. You kind of want to give like an instruction for the machine to be able to learn over time and evolve. So it's not always picking the same algorithm. It's like looking at this task, I collect from my previous memory what's happening in the past and what gives me the best result, and I try this. And if it doesn't work, it's kind of control system, right? It's in reinforcement. You say, next time I'm just gonna try a different thing. Then if you feed a lot of data into it, this machine may really have a good intelligence of what to do. Like very similar to along the line. I think there's a lot of research in that area. So if you search learn to learn, there's I think there's some internet, even Google DeepMind, I think they are doing something like that.
Oh,
Yeah.
thank you.
I think there's a gentleman in the back. Yeah, you. Please.
So you mentioned that feature generation and choosing what features to use, and also data cleaning and preparation is a really important step and takes a lot of effort. Are there any tools or techniques that you'd use to make sure you're on the right track during those stages, or is it more like you do short iteration cycles so you can find out if you're doing the right thing? Just how are you thinking about that?
Yeah, so there are some algorithms that allow you to select the features. So like GTPT, if you feed it in, if you run it for a couple times, you'll actually be able to interpret the feature importance. So you will actually know whether or not this feature has helped. But I think most of the time is about intuition and like learning this. So there's also another deep learning paper. If you're interested, you can look into Microsoft. It's called Deep Crossing. So usually you want to combine features, right? Usually if you have some linear features, you want to do feature conjunction. So for example, for this ad, I don't want to just look at columns where it says like query, right? Only the query vector, but you also want to cross it with the combination of query and the ad domain, right? The advertiser domain. So this is called feature conjunction. So there's a paper called Deep Crossing that actually learns these feature conjunctions for you. So over time, they will try to achieve this by different combinations of the features and tell you which one is it. So that's also along the line of teaching the machine, learning from this thing. But usually, like if it's a manual thing, it's usually your intuition, and you also want to determine whether they are correlating features, because that can really screw things up. So there are some things to watch out for intuition.
In terms of machine learning infrastructure, the computation-wise, more spent on the cleansing side. So you will be using more CPU-based clusters, and I was wondering how does the GPU is used, and how does it? Could you elaborate more on that?
Oh yeah. So that's actually two different parts. Yes. So the first part I was talking about data science is you're usually cleaning the data. The job looks fancy, but usually they're just getting the data ready for the model. But the second half was about the GPUs, or more about deep learning, just because they do a lot of matrices operations, and then their back operation allows more parallel computing. So people are starting to use more GPU for that purpose, just for deep learning's purpose.
Oh.
Usually you wouldn't need a big GPU machine for other tasks, unless they are along matrices.
So when you guys are iterating on the models, maybe it's a model that's been in production for a while, do you spend time focusing more on like adding new features or actually changing out the algorithms, or do you guys have like some kind of ensemble that way you only have to change features and it returns or automatic?
Yeah, it's a combination of both. So I was describing in the beginning that usually everything is ensemble. So you have submodel that's taking care of each individual specific task, because that's when machine learning shines. You don't want to learn too complicated things to say, hey, this is just one task. Tell me more about this author. Tell me more about this app. So usually when we're tuning, it's more like a maintenance mode, right? So you kind of want to know what's happening in this submodel, whether or not you have better features in each submodel. Then you evaluate the entire, you retrain the supermodel, then you kind of evaluate all of it over again. So it's a iterative process, but it's always trial and error. Yes.
From now or in the future, what kind of parameter or algorithm or feature the social media like Facebook user can play around?
I'm sorry, what kind of that we can play
What
around?
kind of like function or algorithm or parameter or feature, whatever people can play around inside the social media now or in the future?
Oh, function, you mean the latest function from Facebook? I don't think I can comment on that. I don't know the product strategy.
Or what kind of machine learning or AI you provide user to play around?
So there are a lot of open source tools that we use internally, but we usually develop something in-house. But we also leverage a lot of the external open source tools. So if you're into deep learning, you can always try TensorFlow. You can, even though it's from Google. And there's also Torch.
No, I'm talking about the social media inside, not the
Oh, but you're talking about like technologies you can play around with, right? In terms of machine learning or just social media features. Is a product problem or a technical
I mean,
problem?
machine learning or AI feature inside the social media. Like,
Oh, you're talking about, it's actually being used everywhere. So you might not know, but a lot of things that you're looking at in your newsfeed, they are powered by these technologies. So you don't know, but they are used, everywhere you use our machine learning. So you open your Facebook newsfeed, what do we show you? What's the first post you see, right? Because we want to be able to, so there's some ranking stuff involved in there. So they are powered by these machine learning models.
so it is possible for the user to play around, or
It's usually no, yeah. It's usually not, yeah. It is, so we kind of want to save some trouble for you, right? We don't want a bunch of options on your phone that you say, hey, don't show me this. But usually you can report when it's really bad, right? You can say, don't show me this in the end. And then that's a strong signal. I think the product side will take care of it. Yeah. Cool, I think I stole most of your time.
That's fantastic. So thank you, Curtis. You said that this slide deck has been approved. It's safe for human consumption. Is it something that we can put up on SlideShare or something and send out to the attendees if
Yeah,
they want
yeah.
to look at those papers?
Yes, definitely.
Okay, thank you so much. That was really great.